Okay, so welcome to the workshop Circulatory System Models, which is going to be an introduction into the package Circulatory System Models, which is a library for modeling, well, the circulatory system, so part of biological modeling, clinical models, but it's also about lumped system models in general, and an introduction in how you can set up your own component library for other applications. So where do we come from? Why did we start developing this library? Well, my name's Thorsten Schenkel. I'm associate professor in continuum mechanics, mechanical and aerospace engineering background, but my research is mostly in biomedical cardiovascular flows. Most of my research has been about 3D models, blood flow in vessels with a view to atherosclerosis risk prediction. So for that, we need to know the three-dimensional flow, but with three-dimensional models, we always need boundary conditions, and that's where my interest in 0D models started, namely the boundary condition for this 3D model here needs to be a pressure response to the flow that goes into these branches. And that drives the distribution of flow between the different branches, etc. So in the early days, we just gave a prescribed percentage on each of these branches, which of course was terribly wrong. And then we started developing Windkessel models, which Harry is going to talk about later in more detail. And I have a few in this introduction. And then we put Windkessel models on each of these branches. And a Windkessel model is a 0D lumped parameter model for the rest of the circulatory system. It's the simplest one we can come up with, but it's a 0D parameter, lumped parameter model for the circulatory system, basically everything that follows on from that branch. And on the other hand, we're now looking into full circulatory system models. On the right side, you see the, relatively well-established SHE model, which has 4 chambers, a circulatory and a systemic and a pulmonary circuit. It has 4 chambers in the heart. It has valve models in there for the 4 valves in the heart, and it's a closed loop model of the circulatory system. The problem that I started out with the boundary conditions for the 3D model was, how do I find the parameters? Because physiological parameters, my parameters for my circulatory system will be completely different to yours. So how do we find these parameters? So we always have this inverse problem to solve. We have some kind of measurement, and then we need to solve the model. So that's where Harry comes in, because Harry's working on the parameter identifiability for these models. So how can we find the parameters? It's an optimization problem. And we need to solve these models multiple times, hundreds of thousands of times, sometimes 1 million times. And that is where we came into this. So that's where Julia comes into this. So this is one of these models that are used as boundary conditions. So what this is a simple 4-element Windkessel model using the electrical analogy. So we have the resistance of the vessel. So here, this is basically the heart, time-dependent source. We have a resistance for the vessels close to the heart, and we have a resistance for the vessels further downstream. The vessels close to the heart are relatively large, so we have an inertia in there. That's this inductance. And we have a compliance or capacitance of the circulatory system to store blood. So we have these 4 electrical components in our system. And if you know a little bit about electronics, then you know that the Kirchhoff laws apply here. So you would start applying the Kirchhoff loop here. Sum of all the pressure drops around that loop is 0. In a connection here, the sum of all the current is 0, if you treat plus and minus going in and coming out. And the pressures are the same. And you build up your system of differential equations. And you do that manually most of the time. So then you end up with these 2 differential equations. And then I ended up, and that's the boundary condition problem that I had. I needed to find the parameters. So if I put that into Python, that looks like this. And my computational time on, not this laptop, this one is a bit faster, but 967 milliseconds on my desktop at home for one solution of that system for 20 seconds with the, what is it, ODE 4.5, I think. And in MATLAB, that looks like this. We all know how to solve ODEs, I guess, more or less. So MATLAB, considerably faster with 130 milliseconds. And in Julia, not only does the code look a lot nicer, in my view, it's also quite a lot faster with 3.7 milliseconds. So that doesn't sound a lot if you do it once, because waiting for 1 second isn't a big deal, but waiting for 1 second for 100,000 times makes it a big deal, because the Python code that I had, I put on our cluster on one node on 28 cores, and it ran 4 days. Not 4 days, but 4 days, so it ran a week and a bit longer to get a parameter optimization on this. In Julia, I do it on this laptop on 8 cores over the lunch break. Yeah. So that was the big deal when I learned about Julia, that why I got into this and why we came here. The second problem I had and that we wanted to solve was derive all the equations by hand. It's not a big deal for the 4-element Windkessel model, but if you go for something like this, which has 88 parameters, I think, well, you'd correct me, please, if that's wrong, but something around 100 parameters, and you do the Kirchhoff loops on that, that's actually a simple one, but if you put coronaries in there or if you put more branches into our circulatory system, then that becomes unwieldy quite quickly. And in particular, if I want, so here we have the systemic circuit, so left heart, systemic circuit, we go into the very large vessels, so basically the beginning of the aorta, then we go into the large arteries, which have inertia in it. So each of these vessels has a compliance, the capacity to expand and store blood, a resistance, and an inertance, the inertia of the blood, because we have large blood volumes. Yeah?
You showed the surface pressure of the vessel. What's your reference measurement of the
The thoracic pressure, we can include that, yes. But we get into that a bit later. Yeah. So then we have arterial capillaries with resistances, etc. So if I want to change something in this, if I have a brilliant idea, okay, let's try if I have, for example, an inertance in the venous system, which may or may not make sense, but I want to try it out, then I have to restart this whole process of deriving the equations. And I don't know about you, but I'm terrible with getting the minus signs in the wrong place if I do that. So not only does it take me 2 days to do that, then I need to check with a mathematician, and then we need to figure out where all the negative minus signs came into the problem. The wrong minus signs came into the problem. So, and that's where acausal modeling comes into this. Because I stole this from the competition, Open Modelica, their presentation. If you know Simulink, then yes, once you have the ODEs, you can put a kind of modular system together, but to me, I'm not a Simulink user, I never really grew into that, because it's basically setting up a block diagram or an algorithm to solve the ODE rather than setting up the ODEs themselves. What I want to do as an engineer is give me a set of ODE equations and then I throw it into a solver. And Chris is here, so we have the best differential equation solvers in Julia that I have seen so far. Yeah? So in an acausal model, we start building these blocks, and that's what this workshop is going to be about. Yeah? We have the library that we built, but if you want a new block, it's relatively easy, for certain definitions of easy, to get a new model sorted. And when you see the code for the different models, then you will see that that is indeed no black magic in here. So when I go back to this, so we will have one block for each of these components, and all you need to do is connect them up. So the tagline is, if you can draw it, you can model it with certain restrictions. There are some rules that you need to follow. So and that means using a library of components, it becomes quite straightforward to set up your own models. So circulatory system models is not the package doing the simulations, or not the package that does all the clever maths. Those packages are modeling toolkit and differential equations.jl. We're just using that. So we make use of the ecosystem that Julia has for scientific modeling and just build on that. So the starting point for all this was the tutorial examples on modeling toolkit.jl's documentation for an RC circuit. That's where I started from, and then we built the whole system around that. So if you have the network, you build your network, or you draw it on a piece of paper, then you have your connection points. That's the first step of the definition. So you know which connections you need. And then you have your component definitions. So the components have their own equations in it. So you need to define the components and the component equations. So the right branch here, that's what circulatory system models.jl has. The left branch is what you need to do. And then you have the system equations, basically solving the Kirchhoff loops and adding all the ODEs. And then the magic happens in structural simplify, which is a function in modeling toolkit, which I describe as a dozen mathematicians in a box, which rip apart all these equations and put them back together. You get an ODE system, which is optimized for differential equations.jl solution. And then you just throw that at any ODE solver that you want. And beyond that, you can then put it into the whole SciML infrastructure for global sensitivity analysis, for the parameter optimization, global optimization, local optimization, etc. So what we'd want to talk about is basically this left branch, and then a little bit about how you can define your own components later on. So just a quick demo, not want to take apart here, away from what Harry's going to do, but just quick show how that will look like. So this 4-element Windkessel model, without knowing the ODEs, I set it up in defining the components based on the libraries that I have. Sine dichrotic is just a time function. I define a function in time that gives me the flow. Resistor, inductance, resistor, capacitor, ground, all named. And then the connection happens here. I have 3 connections, one here, one here, one here. And one here. But that's the connection network here. And that's written out in these connect definitions. That gives me an ODE system using these 2 lines. And that's now a system with 32 equations. Structural simplify will break that down into 2 equations, which may or may not be the same that we've seen in the other slide, because structural simplify may optimize it differently. And I found it's optimizing it better than I can manually, annoyingly. And when I solve that, then that's the code for solving it. So after this point, it's just a regular ODE system. If you have to find it by hand or not, after this point, it's all the same. So the ODE system, circsys, is then solved with initial conditions and a time span, and I'm now down to 1.7 milliseconds. Remember, it was 3.8 milliseconds with the hand-derived equations. So I don't know where that ×2 speedup comes from, but it's there. That's all on the same machine on the same afternoon, so these benchmarks. But I'm now down from 1 second in Python, 970 milliseconds to 1.7 milliseconds, and that's the magic. Not taking credit for that. That's all the magic that happens because of the SciML ecosystem. We just made it more easy to use for circulatory system models by building that standard library. And maybe ultimately it's going to go into the modeling toolkit standard library, but that's maybe a unit problem because we're using weird units in physiology. So we have all these predefined components. That's what the model is for. We have compound models. I'm just going to give you another example for that. And you can easily define your own components. A lot easier than in some other frameworks that do that. Modelica may be the closest comparison here, but CellML is a lot more difficult to get the components defined, for example, for those of you who know that part. And well, we have validated it against hand-derived ODE models, against published data, etc. So it should do what we expect it to do, always. Check your own simulation models. So for the full model, we're going to go through that in detail, so I'm just doing very quick and brief. So we define chambers, we define valves, she chamber, she valve is all predefined in the toolkit. System loop, SAS, SAT, SAR, SCP, that's capacitances, resistors, and so on. That's this branch here. Pulmonary loop, and we connect them. Obviously, that connection function block is a lot longer for this model. And then benchmarking it against CellML, which is another popular modeling language, I say, for this kind of stuff. We get from 6 seconds down to 170 milliseconds for a run on this model. Or 57 seconds, I have to say, because we have compared to Python before. So that is the speed up we got for this complex model. Just a brief thing in compound models. So we can set up compound functions, and we're going to show you how you can do your own. So this is a compound function for the whole systemic loop, which basically looks like the main system itself. It's just inside that function block. So you can use that instead of building the same system over and over again. You can just define your compound modules. And yeah, and the big benefit over hand deriving your ODEs with a model system, with a modeling library like this is, if I want to change the heart valves, we're doing some research in which heart valve models are better suited for these models. It's a 4-line change. Well, obviously you need to define the equations for your heart valve model. That's a bit more than 4 lines. But if you want to just check, okay, how does my system behave with a different valve model? That's changing 4 lines of code, namely these 4 lines, and then the rest all stays the same. And that's what we want to look into in this workshop. That's not interesting for today, but that's the brief introduction. So I'm going to hand over to Harry, who is the co-developer on this and main user at the moment. And yeah. Mm-hmm.
And we know the values of those capacitors.
Yeah.
So really natural if you want to do the resistance. For example, if you show the section that the parallel resistor, if it's too small, then it short circuit those kind of
Yeah, exactly.
How do we do this kind of resistance to come up with that?
Yeah, well, this is obviously the result of a system that had parameters optimized. So we, for example, can take, and that's what Harry's PhD is all about, we can identify which parameters are influential and which aren't by running sensitivity analyses and optimization problems on it. There will be parameter combinations that blow up the whole system, obviously. Yeah? So, and you need to do keep a few good practice guides in mind. You can't just put 2 compliances next to each other. So if you connect 2 compliances, then that's mathematically an ill-defined problem because they can just start developing an oscillatory instability, you need to have a damping element in between, so you need to have at least a small resistor in between. So one common thing in these models is you keep the compliance of the venous system and the compliance of the atria together. You can do that, but then you need to derive a different ODE for it. If you do that in the A-causal model, if you just combine the vein compliance and the atrial compliance together, that's going to blow up the ODE system mathematically. So that becomes unstable. So, or if you short circuit something because your resistance is too small, and then that can lead to instability. So the usual problems with ODE still apply. This is not going to solve that kind of problem. So if you do a global analysis of parameter optimization, there will be parts in your parameter space where you just don't get a solution, or where you need to move to a stiff solver or something. But if you leave the solver choice open to differential equations JL, that will most likely solve part of that problem, but not all of it. But you may need to switch to different solvers for different combinations of parameters. So it doesn't solve the problems in solving the ODEs. That's further downstream. So if you have if you have a stiff set of parameters, then it becomes more difficult to solve the equations. And the times I showed you here are the times for the parameter set that we have defined that are physiological. If I move away from that, we had some parameter sets where those 2 milliseconds suddenly became 2 seconds, because you need to switch to the differential equation JL will switch to a stiff solver and then just solve for that parameter set. That solution takes a lot longer. So this is not, so if you do an optimization, you can't say, okay, I have 100,000 times. That's 2 milliseconds times 100,000. There will be parameter sets that take a lot longer than that. So your average, that's not the average solution time. That's the average solution time for the optimized parameter set. So we have all these problems indeed. Yeah. Okay. Any questions so far? Again, still? If not, I introduce Harry.
So, hi everybody. So I'm Harry. First order of business. If I slip into my kind of dulcet Yorkshire tones and nobody can understand me, please shout out. Because if students in university struggle to understand me, people from the US and elsewhere might also. So
it's all right as long as modeling is spelled with one L.
Well, exactly. I like to assume he did that for a joke, but yeah, so Torsten gave a really nice introduction there about kind of why we are interested in developing these kinds of libraries. So I apologize for the kind of the hackness of the images and the kind of alt tab that's going to be going on. But I think it's all really about you can get kind of caught up in your own sphere, and it's when you try and move into kind of clinical practice. We spoke there a lot about deriving these equations and working these out, but the feasibility is clinicians just want answers. They want something to say, okay, well, but I think it may work in this certain way. And instead of going back and re-deriving everything and reprogramming everything and having another meeting in a week, we can do that in 2 minutes or something like that. Okay, so we'll start, because I'll maybe labour the point on some of the modelling toolkit things as we've got some kind of newbies here, but we'll start with looking at this simple kind of CR circuit that you can find in the modelling toolkit documentation. I think it's important that we note a difference as well. Is often these compliances here are usually represented as capacitors also. There's not a world of difference from this. But what modelling this as a compliance, so a chamber allows us to attribute a volume to this. So you can keep track also of the blood volume in the different compartments and different chambers that are in the circulatory system. So from the code that's on GitHub there, so we'll start just by defining this input function here, this I sign. If I plot this, this is just saying, okay, well, we've got some sort of flow, we've got some sort of contracting heart, really dead simple, and we'll go into more advanced models of this further down, but we've got some sort of response, contract, then nothing, contract, then nothing. And so on a real kind of simple level represents this beating heart. So we define then just the source. So we say, okay, this is going to be just some sort of driven flow, an amplitude of 100, and the function that's driving that is this I sign here.
For the link comments, well, and those who don't have 120 words from the first line, the code is on GitHub. The GitHub address is over there. You don't need to try and put this in.
So we've got then the driven flow there representing that beating heart. So we then had this resistor. So we've got a resistor in the circuit, and there's just an element there, resistor, along with this compliance. And then we've got a ground. Well, started already. And then we've got this ground where the system's going to complete. So each one of these is defined within the library in terms of the physiological components that we're interested in. So we'll go into this a little bit more further on, but we define there just the equation for the volume of the chamber, and then from that we can work out the calculation for the derivative of the pressure there. And then starting, we're defining we spoke about Kirchhoff's laws, so flow in, flow out, represented here by in Q and out Q. And then we also define a delta P, which represents the pressure difference across these different compartments there. So, and the resistor, we're just writing there, just the simple equations for the resistor. So, compliance ground, and this is then where the kind of the real meat of the package is. So we've got the source coming out, so what we want, source out, and that goes straight in to the compliance. So we can define that as the first connecting statement. Then, well, what goes in the compliance has to come out the compliance. So we've got out flows into that resistor there, and then flow out of the resistor, and as well as the input to the source, all lands on the ground at the end of the circuit there. So all ended up in this ground here. So we can connect them, compose the ODE system with the time, and then if we simplify, structural simplify, I've already pre-ran this, so it's really quick, but caps lock. So there we're just left with one equation that dictates the entirety of the system, and that there is then just the pressure for this compliance, and we can see we've got the equation there, which is flow in plus flow out defined as a minus, and then divided by this compliance here. So if you want to access all the other equations of the system, we've also got them in there, and so every equation that you would write out by hand is then also stored in the observed there. So you still can get what you would get through deriving this by hand and on bits of paper, but the structural simplify returns to you the important equations that allow you to just simulate this system. So we give it initial condition, compose the ODE problem, solve it, and then we can plot there, and we've got this transient behavior in the beginning, but in the end, it then stops into a steady flow that would represent some sort of pressure if we played around with parameters to get it to a normal value. So this is the same process that we go through every single time in composing these systems. Okay, what do we want to add, and how can we examine these outputs? So the next step up from this 2-element Windkessel would then just be to the 3-element. So moving to the 3-element Windkessel there, again, we've got parameter t, an input function, which is just then this driven flow. But this time, we've now got a proximal resistance and a characteristic resistance. And from before, we had then the output of the source was connecting directly into the compliance. So connecting directly into the compliance, instead of this time, we've got the proximal resistance there. So we could have just copied and pasted this code above. Where were we? Could have just copied and pasted this code above and added these additional connect signs. But what we've got this time, we just say, okay, we want to add this proximal resistance. We're just going to say it's this resistance, and it's got a value of 0.1. And we just add, the important part is these connect statements here. If we can get these connect statements correct, and we can tell the fluid where it's going, then you can simulate your system in exactly the same way. So we compose, ensuring we're adding this proximal resistance, simplify that model, and we can solve as before. So we're just there plotting. If you just say, okay, plot the solution to this system, you're only going to be plotting the main equation there that is chucked out of structural simplify. If you want to access any specific variables within your system, so if you say in a daft manner, but if this proximal resistance might signify resistance across a valve or resistance in a vessel, constriction in a vessel, and then you get some clinician who says, okay, well, how's the flow affected in that manner? You can just access that variable by saying, okay, well, we've called the object RP, proximal resistance, and we want to access the flow element, so that's just then RP.Q, for which we can access that. But there we have kind of a proximal resistance that is more or less similar to the input flow that we got in the first place. Yeah. So we then move to the more commonly used Windkessel models here. So we're going to show, okay, so you've got two different 4-element Windkessels. We're going to have one that's got this inductance in series, and we've got one that's placed in parallel. If we then try and compare the two codes, how do they actually differ? So we'll first look at the series Windkessel model. Once again, we've got the input function, driven flow, and this time we've got the inductance. So the inductance L, well, exactly the same way in what we changed the 2-element to the 3-element Windkessel there. We have, well, what's coming out of the source, and that goes into the inertia, the inductance, and then flow out of the inductance into the proximal resistance, and so on and so on. So connect them equations, and it's the same process every single time. The only thing here that's changing is we're adding an additional element, and we're connecting in a slightly different way. So we've added the additional element in the connect statements. We've added this to the compose. And we can simplify that. So, but then that solves, and we get the equations. And we get the results there for the individual variables. And we were talking earlier about compliance allows us to access the volume of a compartment. So we can call that the volume of the compartment by just the variable name .v. And that's accessing compartment C and the volume of that there. Okay. So now we were saying, okay, we want to move to the parallel Wind-Kessel model. So appear to have omitted that from the workshop, but let's do that anyway. Do it on the fly. Famous last words. So I'm saying, okay, I've got the code for the series Wind-Kessel model. How do I then change that to the parallel case? So we've got the input function. That's going to stay the same. Well, we're not adding any additional terms, so they're just going to stay the same. But we then need to look at, okay, well, how does the flow move through this system? And this is where we change the lines in the code. So, flow out of the chamber is going into both the inductance and the proximal resistance. Well, here we've got flow out is just going into the inertia. We need to change that. So, well, the outflow then is then going into the proximal resistance and the inertia at the same time. And that makes intuitive sense by just, we've drawn it, we want flow in to go into the inertia and the proximal resistance. Okay. So, well, flow into them has got to come out as well. So we want the flow out of the inductance and the flow out of the proximal resistance. That's going to then flow into the compliance there. That's going to flow into the compliance there. That's brilliant. And we can get rid of that line because that was hanging on from the series connection. So now we've got flow into both the parallel combination, flow out of the parallel combination goes into the compliance. And we've got, well, the rest of the circuit is exactly the same as before. So flow out of compliance into the characteristic resistance, out of characteristic resistance, brilliant. Nothing's changed from the series code, as that was, no components have changed at all. But this time, we've now got two equations, and we can examine them. So we now need to give two initial conditions. So we've got initial pressure, we're going to give just 9, and then an initial flow through that inductance, just say 0. And we can solve that problem there. And there we see we're plotting then the two equations that have been kicked out. But the thing I want to say is there, and maybe I planned it, maybe I didn't, but we took the series 4-element Wind-Kessel and we've said, okay, I want you to change that for me almost immediately. And in doing that, we've changed what? Two lines of code in doing that, and it's not been, there's been no kind of grand task in doing that at all. And so that ability to chop and change to different systems quite quickly is quite a nice one. Do people want to play around with Windkessels for 10 minutes? Just to try and get that before we move on to the more physiological thing, do you reckon? Yeah, have a play for 10 minutes with this code, and then we'll move on to the...
One thing that I think is interesting at that point, and might have been lost for some, if you just bring the equations up again. You don't really know which equations modeling toolkit is going to kick out from for you. So it's always needed that you check the equations, so you know which boundary condition, which initial conditions you need to define. Because what structural simplify does is it's going to take the whole system of equations apart. We look at it has 32 equations, of which 21 are ODEs. And then it takes those apart, takes the unnecessary ones out, puts them into the observed equation set, and it puts the two that it wants to solve, or that you have to solve, into the equation set. And there are multiple different ways to do that. And Modeling Toolkit doesn't always give you the ones that you expect. Because this is very similar to the one that I had earlier, and you've seen my equations, and they were both in pressure. Because if you do it manually, you tend to try to get both in the same variable. So I derived equations dp dt, dp1 dt, dp2 dt. Here we get one in p and one in q, and we've seen that that is twice as fast, and that's why. Because this system is easier to solve than the one in 2p's, but you never know what you get. So it's always important that you check what your actual equation system looks like, and then define your initial conditions accordingly. And it may also come out in another order, but there are ways around that with parameter lists, etc. But you don't know what your parameter order is, and you don't know what your equation order is at that stage after the structural simplify. So that's, if you do it in a prototyping way, it's always important to check that at this stage. No, it's not two parallel resistors. One is an inertance. So that's the inertia of the blood. And one is a resistor. It goes around the tube, it kind of hits the side and then suffers this kind of stopping motion. Yeah, so it looks like, it looks similar to the American version of the resistor, I think, but it's looped, and that's the inertance. So the resistor doesn't have these little loops at the bottom. So it's not two resistors that in parallel, but one is an inertance which takes into account the speed and the mass times velocity squared in there. So the ODEs look different. So the ODE for the inertance is the lower one, and that's basically minus P over L. Well, so dq dt is minus P over L, which is the inertia equation. And the other one is the compliance equation, which is basically change in volume divided by C. Yeah. Is the change in pressure. The equations that are in the library there are then just Ohm's law for the resistor, and the inductance is dq. Oh, okay. dq is then equal to the dp divided by L. So there is a change in the, it's not just two parallel resistors. Yeah, otherwise the system would optimize those. Yeah. You would get one over R1. Yeah, if it was two resistors. This one. Just hold the parallel. you can just do that quickly.
What? Two
If
resistors.
you define it as two parallel resistors, then I don't know what the system's going to do, but I would expect it to just take that out and have one resistor term in there with 1 over R1 plus 1 over R2 to the power of -1. So let's just check that and replace the inertance with a resistor, and then it will optimize it, simplify the equations accordingly.
Yeah. So if I then just change that to an
Just R1.
R1.
So just that change, make it L and R1. L and R1, and then we should
But it gives you an algebraic equation.
one is an
Yeah.
algebraic equation.
So you end up with an algebraic equation there between the two resistors. So there's not another differential equation that's driving this system. So the algebraic is just a constraint essentially, just saying okay.
That's just the constraint that the
sum of the flows
is the same flow.
Yeah. So that's there, just saying okay.
So
They're optimizing them, just saying the flows there have to be exactly the same as what's coming in.
And as far as I see it, that's one of the beauties of A-causal modeling. You don't actually need to worry about the whole, how do the ODEs come together. You don't need to know about the ODEs in the first place. So you need to know that it's going to end up in a system of ODEs, and then you need to know what to do with a system of ODEs. But the construction of that system, you don't need to worry about that. And that's the beauty of modeling toolkit in this case. If you give it an ODE system, and you could do that in the hand-derived version.
Yeah.
The first step in hand-deriving this is just composing all the ODEs together, and then you end up with, in this case, 30-something equations, and then you can do that structural simplify step on a hand-derived ODE system as well, instead of doing that simplification and elimination of variables yourself. And if you've done this, stuff like this in MATLAB, you know the step that you simplify your ODE system, and then afterwards, after the solution, you have a new function that basically calculates all the observed variables, and you don't need that with modeling toolkit, because the simplify step creates those two sets of equations, one that gets solved in the solver, but the solution object has all the algebraic equations for the observed variables in the background, so you can interrogate those as well. Mm-hmm. And Harry took advantage of the plot module, the plots.jl package, actually it's modeling toolkit, has plots templates or plots recipes for their solution object, so you can just use that IDXS keyword to just ask for which variable you want. And you can make that a vector, so you can plot multiple variables in the same plot, or you can plot one against the other. So if you make that a tuple, I think it plots one against the other. Yeah. If you make it a vector, it plots it all against time. So the plots recipe for this is also for modeling toolkit is quite useful in this context, because it has all the observables in that system as well. Not only the two states, or one state in this case, but also the whole set of observables are available at that point.
Yeah, I think it allows you to spend longer worrying about what's actually in the system. So you know what variables you're going to need, what are the outputs that you want. And using this allows you to say, okay, well, I'm going to chuck all the equations to the back because they're already in the system. Let's focus on the application of which these are.
Actually, should we go into showing how the elements are set up? So what happens in the background, what happens behind the scenes?
Question about when you set up
Sorry.
With the U0 term, I think you use
Okay, so when you set your U0 initial conditions term, how do you know kind of what those numbers correspond to in the bigger model?
That's why Harry, every time he does a structural simplify, does an equations,
Yeah.
calls the equations function, because the equations and then your system, which would be equations circ-sys, wouldn't it?
Yeah. So this here allows you to say, okay,
That gives you the two equations. And that shows you in which order they are. So in this case, we need one boundary condition for the pressure in the compliance. In the previous case, we had one boundary condition for the pressure in the compliance and one boundary condition for the flow through the system.
You can also ask for the states.
Yeah, you can also ask
Yeah,
for the state.
Easier.
Yeah, true.
You don't know which
Yeah.
variable is.
Yeah, true. Yeah, for us it's the same, but yeah, that's very true. The better way to do this, if you don't want to see the equations, just ask for the states.
yeah.
And that gives you the two states that it solves for. Thank you for that. That's
But one thing that I'd be cautious with there, looking at the equations, allows you to identify if any of them are algebraic. Because if you were then to specify, you can use this ODE problem. And what that allows you to do is only set boundary conditions for the equations that are defined as differential. So this one here would still solve with only one boundary condition because we added that additional parallel resistor there, it created this algebraic equation. Whereas if I go to the previous one, so previous one there, we look at the equations, the states would give you that, but if you look at the equations, you've got two, so you need two boundary conditions for each differential equation. If it's an algebraic equation, you don't need to specify an initial condition because it's just essentially a constraint on that system. So the whole system will have that constraint applied to it at each time step.
And it may be that's because I usually stick to the ODE system, which technically is the wrong definition for that second system we had with one ODE and one algebraic constraint. But the solvers in differential equation JL are usually clever enough to just sort that out for you. So I usually just keep that as an ODE system and define two initial conditions, whether that's an algebraic or not. So I would go for the states. Just look at the two states, define initial conditions for those two. Even if I didn't need to, if I look at the equations and see that there are algebraic equations in there, count the ODEs in the order and give the initial condition. So you have two ways to look at that. So you can look at your system and then decide what's the best way to solve it, which may give you a bit more optimization options. But if you don't want to worry about that and just want to have a quick change in topography of your network, just make the change, leave everything as it is, and just throw it into the ODE problem and let differential equations JL do that magic in the background. There are some solvers that don't like ODE systems, but most solvers, and my favorite solver is the Vern 7, that just takes everything you throw at it.
Yeah, I mean, just like I was running this a bit, and I looked like I can even put a negative close to start with. Like it doesn't really keep the initial.
So there's an example with the capacitor as well. So the capacitor is defined in delta P.
Yes, one thing that we need to keep in mind, this is not electrical. We use physiological variables, and I mentioned that briefly in the introduction. The variables are on the documentation, so the pressure is in millimeters Hg, because it's the physiological pressure, and flow is defined positive into the element, negative out.
So that's why we've got that negative to start with.
The pressure difference over an element will usually be negative. So it's not the potential definition as you would have it in the electrical circuit, but it's the flow physiological definition of pressure drop being negative over the resistance. That's is important when you look at the values. There might be a negative sign somewhere, which comes from that definition how everything is set up.
So that's why I try and avoid using the capacitor where possible, because I think it introduces that additional delta P, which sometimes can cause
that can
confusion.
Be very confusing, because if you, when we have this system for the compliance, and that is equivalent to what you could use like that. So this would be in, and that would be out, and that would be in, and that would be out. But from a physiological point of view, that's much more difficult to actually evaluate later on, and that also doesn't give you the volume. So that doesn't have a volume in it. So obviously, from electrical analogy, you can figure out what the charge of that capacitor is at any point, which would be equivalent to the volume. But it's not usually done in the Witt-Kessel models, if you use a dangling capacitor, as we call it. Mm. So if you take this, then that is basically the definition of this compliance. And another definition that we have is the elastance, which is the same thing, but you can have that as E, and then E is 1 over C mathematically. That's just a different definition, which is also very often used in physiological models. And we use the elastance in the ventricular chambers, for example. So, because they are usually defined by the elastance of the material, which then is not volume over C, but volume times elastance. But it's all the same definition, basically. So when we go through the elements, you will see some defined as capacitances, some defined as compliances, some defined as elastances, and they are.
Well, should we look at the Nicolai model? I think.
Yeah, we can do it.
Yeah, and then we can look at the elements there.
Yeah.
So this is a kind of a really well established. It's an established model for the systemic circulation. So they attribute an elastance, which we'll look at in a sec. So they attribute an elastance there, which is the left ventricle. So this controls the mechanics of the kind of the powerhouse of your heart. So how that contracts and the volume pressure changes. The diodes, they're represented in heart valves in the system. So we'll see how they're defined, but they operate on a pressure gradient and then open to let flow through and then close. And then we've got a CRC circuit, so representing the compliance of systemic artery, then systemic resistance, and then the venous capacitance there. So we'd expect to see values where the venous capacitance. The venous compliance is much larger than that of the systemic compliance due to it essentially just being a massive pool of blood there. And so in this system, we ignore the pulmonary loop, but we'll look at the full sheet that was shown in Torsten's introduction. And that then just feeds straight back down through the mitral valve and into the left ventricle there.
So, and if you prefer to think of these compliances in terms of how elastic or how stiff, let's say, the vessel walls are, then you can just turn that upside down and say E is 1 over C. So a large compliance means a low Young's modulus, basically. So depending on which physiological definition you're working in, you can replace those then with different elements which will give you different values. But it's the same ODE in the end, because one parameter can be expressed in 2 different ways. We have different elements for those 2 times. So the veins are much less stiff, so they can store much more volume at much lower pressures.
So we can set this up. I'll set it up first initially as a kind of a standard ODE problem that people would probably write. So, and this is a kind of a fairly naive first pass setup of writing the equations in this way. So we define a function which is going to be the heart valve. So we say, okay, if the here we've got a negative sign arising there, like we've said. So if the negative of the pressure difference is less than 0, then the valve opens, and what we get is we've got the pressure difference across that valve divided by the aortic or the mitral valve resistance. But otherwise, that valve's going to be shut, and that then means just no flow's getting through. We assume infinite resistance.
So you're assuming that on-off.
Yeah,
no area change.
No, not in this simple one.
we'll look at a more advanced one and how we write that later. So just on-off, which is the standard in most lump parameter systems. If it's open, flow through divided by the resistance. Otherwise, no flow at all. And we've got then here the functions for the elastance. So I'll just flip over onto that. So that would be then the kind of the mathematical definition of the heart valve, the pressure difference and the resistance across that. And so controlling the left ventricle, we have the elastance.
We are looking at elements that are already defined at this stage. So you don't need to do that. The She elastance is already defined. The diode valve is already defined. We're looking into what's behind the scene. It's all written in Julia, so there's, as with most modules in Julia, you can go into it, just copy a function out, change it easily. And so we're under the hood now.
Yeah.
So if you want, for example, to find, and we're going to do a little example later on with a new heart valve function that we're going to implement directly, which is not part of circulatory system models at the moment. And then you can see how that works. So you can go about these in a few different ways. The valve function, the Q function that Harry defined here, Q as a function of delta P, can be anything. And it can be, as we will later see, also a time-dependent differential equation function that can be built into this whole thing, but I don't want to go too far into the future here. But the elastance here, that is as published by She 2006.
Yes.
And that is just directly implemented in that She elastance function, which is then used in the definition of that She ventricle ODE that is in the element. Mm-hmm. So we have the elastance function, and we have the ventricle function, which uses it. I think that's...
Yeah, I'll show them
just
that.
for the context. So this is not part of the actual modeling. We go beyond that now. And if you want to implement your own elements, then that is how you could do that.
So valve, She elastance, and then we've also got the derivative of that elastance. Anyway, we've got the parameters. So we'd set up the equations like this. We've got the first differential equation, which is for the left ventricle, and that's written in terms of the pressure. So you've got the elastance, but you also need to define that derivative because, well, you've worked out the equations, you know what you need, write the functions that do the job.
So this is the hand-derived?
Yeah, the hand-derived. And then hand-derived equations for the individual components also, hand-derived equations for then the valves. And so, because this is then an algebraic system as well, a DAE, solve using the mass matrix, and then this is all in the differential equations, but the plots so, and then you can plot that, and you get a system which looks quite physiological in what you would expect. So, hand-derived, we're now going to move to using circulatory systems, and how's that done? So, define parameters again, but this time we want the She chamber. So, that's already predefined in circulatory systems, and it's got a set parameter list. Give it them parameters, and then you don't have to worry about the equations that are behind that. So we say left ventricle is that then the sheath chamber. We've got two valves in this. So, well, that's called by just resistor diode. And so we say the resistance is then just that across the aortic valve, and then that across the mitral valve.
Resistor diode, because in the electrical chart we had a diode, but it's not an ideal diode, because we have two compliances either side. Do we have a resistor? No,
so it's two compliances either side.
So we need to have a small resistance at least in the middle, and a real diode and a real heart valve will have a resistance. So that's not a loss in fidelity.
Yeah.
But just keep that in mind that we need to define a resistance at that point, because combining the ODEs for two compliances doesn't work, because that gives you an unstable system.
Yeah. So resistor diode, and then we define the systemic arteries compliance, venous system, and then the systemic resistance. And so instead of hand deriving the equations as what we've done above, we sit with that in front of us, and then we think, okay, well, what direction is everything going? So flow out of the ventricle goes into the aortic valve. Flow out of the aortic valve is into the systemic compliance. Out of the systemic compliance goes down into systemic resistance. Systemic resistance out into the venous system out into the mitral valve, and the mitral valve feeds that back round into the left ventricle. So there's a complete loop that's established in these equations. So you should know you're onto something if kind of the first one you write up there, left ventricle out, should always be kind of left ventricle in at the end, because you need to make sure you've joined up this loop every single time for these lump systems. So we can connect them, compose the systems.
36 equations?
Yeah, so
which are ODEs?
So if we looked at, you can look at them, but from that, you're very difficult to interpret and understand them. So we structural simplify and reduces that down to just 3 equations there. And so by looking at the equations, we've got 3. 1 is for left ventricular volume, 2 are for the compliances in terms of pressure. But if
and here again, the hand-derived one was in pressures only, wasn't it?
yeah,
Modeling toolkit gives you a different optimization very often. So here we have a mixed volume pressure formulation. Can control that somewhat with how you define your elements, but it sometimes turns out to give you different optimizations for the final system.
so we're specifying the initial conditions there based on what equations have been returned to us. So we can have a guess at, okay, well, what would be the left ventricular volume, the systemic arterial pressure, and then the pressure in the venous system also. So we can solve that. And we're returning the 3 variables which were in the equations. And like I said before, if we want to plot things, we want to plot things individually, you can just specify that using the index keyword, and that returns to us, okay, well, what's the flow through the aortic valve? We got aortic valve.q. We can look at venous volume and aortic pressure there. So just through going from the hand-derived equations, and quite often people would eliminate them last 3 anyway. Because that's me just writing out the equation individually, that's me not eliminating any variables there at all. So
You could try a live that system for structural simplify, will you get the same ones?
It's not symbolic then, is it?
So, okay.
Yeah. So the comparison between the hand-derived and the symbolics is that point that we've been banging on about before, in that if you want to add an additional element or you want to change the way in which a valve works or something like that, it's 2 lines of code that you may change. And your biggest worry then becomes, where do you put your initial conditions? So we'll look under the hood at what was going on. There we are. So
maybe start with the pins and the
start right here.
So the fundamental element in all these A-causal models is the connector, which is in this case a pin, which has variables pressure and flow, and the flow is defined as flow being variable. That defines which part, which one of the Kirchhoff equations are solved for this variable. Then we have a basic element, and this is straight out of the modeling toolkit tutorial, that's not our invention. We have a basic element which has 2 pins, an in pin and an out pin, and something in between. And that just defines a few things. It defines a pressure drop over the element, which is defined as delta P tilde, and we use the tilde sign instead of the equation sign to define symbolic equations in these elements. So just read the tilde as an equal if you write out your equations. So we have the equation delta P is out P minus in P, which gives you a negative pressure over the element, which is different to what we would do in the electrical analogy, where you have the potential in minus out. So keep in mind that delta P is usually negative. And we have, in this case, it's not a compliant element, this one port. In must go out, and Q is defined, the flow is defined as in Q. So that will be the basis for the diodes, for the valves, for anything that is not a compliance. Then that's the basic equation. If we now go to the resistor, then the resistor has one equation more, only one. So we define it based on the one port. So that first line just takes the one port as the base element, extends it, a bit like inheritance in OO, which I don't understand at all, so not an OO person. So we unpack the variables that come from the one port. So we have delta P and Q now. We have a parameter R, the resistance, and the additional equation is an algebraic one, namely that the pressure drop over the resistance is minus Q times R, the minus sign for the negative pressure. That's the additional equation that I need to define a resistor, and that's it. The last line just returns the new system, which extends the system that I have for one port with this equation. So the resistor function returns an equation system that is the 2 Kirchhoff equations, not the Kirchhoff, sorry, the one port equations plus this one equation that makes this one port element a resistor. Yeah?
I noticed that this is not defined as an add component, but it seems like it's basically an MTK component, right?
It's an MTK component, yes, correct.
But is there a reason that you didn't define it as a component?
What do you mean?
So there's usually this add component macro that...
we did this before that macro existed. So we may change that in the future, yeah. And if you go to, let's have a look at the capacity, the compliance maybe. Capacitors is not very interesting because we usually use compliance. The compliance is basically defined from scratch. Yeah? So it's defined with an in pin, with an out pin. It defines the variables, volume of the compliance. It defines the pressure of the compliance. And then it defines the equations that describe this compliance. So that's just, we only need to worry about this one element because all the composing is done afterwards. So this element has a pressure drop, pressure in minus pressure out. No, sorry, it doesn't have a pressure drop because it doesn't have a resistance. Sorry, getting confused here. So if you look at the first equation, 0 is in pressure minus out pressure. So in and out pressure are the same. So we have one pressure defined for the whole system, which is defined in the next equation. So we can call for it later on. And then we go for the definition of compliance, which is volume is pressure times the compliance plus the initial unstressed volume, not the initial, the unstressed volume, V0, which is a parameter for this element. And then we have the differential equation that describes the compliance, which is the differential in P is change in volume, which is the imbalance between in and outgoing flows, divided by the compliance of the element. So that's what's going on behind the scenes. So this is now inside of CirculatorySystemModels.jl. And then if you go for the elastance, that's just the same thing, but the last two equations are slightly different. The volume is defined as P over E, not P times E. P over E plus V0, not P times C plus P V0. That's the difference, because compliance is just 1 over E. And then we have dP is the change in volume times the elastance. So that's just, so we can use elastance and compliance for the same element, depending on what you want to define it as. It's going to end up with the same system. And if you go for the let's have a look at the ventricle, because that's a bit at the chamber, because that's a bit more complicated. No, yeah, that was
double.
No, there we are. So the chamber is basically the same thing. So P is P0 plus B minus B0 times E. So we have an initial pressure, we have an elastance defined, but E is defined externally as an external function, which is the function that Harry showed earlier.
That's just down below.
We did a manual derivation of the shear elastance because that's a bit quicker, having automated, or having it differentiate inside of the element. But if you don't want to, if your outside function doesn't, then you can use all these clever automated differentiations tricks that are available in Julia as well. But in this case, we define both the elastance and the derivative in time of the elastance directly, because we need those in the differential equations. So we have, do we need that? Where is that?
Not the derivative.
We don't need the derivative in this case, do we? No, not in this one. So that's the two equations that derive a hard chamber, which is essentially the same as an elastance with a time varying elastance. So that contracts and relaxes over time. And you can have, and there are any number of different definitions how that contraction relaxation cycle is defined. One of the traditional ones is a double hill function. You have two functions like this, one like that, one like that.
Yeah, so that's.
So you get a rising and a falling rank, and the shear function is basically two cosines combined. And that's why we defined that outside of the function, because you could make this a bit more elegant by defining one chamber and then just giving it the function that it needs. But yeah, the double hill function is a bit more complex.
Yeah, so as Torsten said, we've got then kind of any number of, we've only got two so far, but there's plenty of other definitions in terms of exponentials and things like that, how to define the kind of contractility of this ventricle. So if we just want to say, okay, we're going to change the definition of this left ventricle, How do you do that? So you just say, okay, we're going to change that to double hill. We've got the resistors for the valves.
Show the equations with that. They're going to
Yeah.
Because it's symbolic, it will take that elastance function and just carry it through into the differential equation. So reading those as a human is a bit tricky, but it just carries all of that through. And some of these definitions will have if-else's in or Boolean operations, and all of those get carried through to the ODEs. So if you're very deep into that symbolics JL usage, then all of that is still available at the end of this chain.
So we get exactly the same results there for what we had in the first instance, but this time the equations are in pressure, so we get left ventricular pressure, and then the orange is the aortic pressure over the top of that there. So I think if we, where was that? There, and that's there just the definition of what the double hill function looks like there.
Double hill function is a bit tricky to get your head around, so we don't want to go into the details.
Yeah, no,
if you need that double hill ventricle model, which is quite common, then that is available. There's one additional step that's required if you want to use that, because the two double hill functions, if you multiply them, they don't end up on a maximum of 1. They end up on an arbitrary maximum. So you need to do a maximum find first, which is one of the lines in your code.
Yeah, she's just about
Because
finding.
There's a scaling parameter involved. And we try to do that inline, but then that maximum find has to be done while the ODE is running, which makes it slow. So we do that up front. So if you use the double hill, there's this one additional step that you need to do. Define it as a parameter, this k, because that is a scaling factor that is constant for the whole thing. But it makes it slightly tricky to use later on, because if you change the parameter set, you need to do that k calculation once. If anybody who knows modeling toolkit better has an idea how we can make that maximum find internal inside the function and only do it once for each new parameter set, that would be very welcome. Because at the moment we get 2 or 3 orders of magnitude slowdown if you do that inline.
So we were talking. So we've written out the equation completely there. So what happens now if we want to say, okay, well, can we combine subsystems together? Because that's still a very this system there is still very simple system. But if we want to extend to things like that or like that, you're going to quite quickly begin to trip over yourself. But it allows you to also gives you the kind of the user control over what elements you want to change or what you want to play with. So we're going to say, okay, we want to combine that circulation together, just as a systemic circulation. So we just quite aptly call it CRC. So this is then just the combination of compliance resistor and another compliance on the other end. And so how it works is essentially the same way as when you're deriving the system in the first place. But this time you're working from the pins that we defined in the back end up here, which just control the in and outs that go through the system. So we've got 2 variables in this. We'll have the delta P and the flow. And quite importantly here, we define this PS as just to be empty. This is quite important, when defining another element on top, because we want, these are compliance resistor and compliance. They're already predefined within the circulatory system models. So we want the parameters that we define here to be inherited from the compliance resistant compliant. We don't want to define the parameters twice, because if we had parameters here and there, you'd end up with two parameters which are the same, and that's just a headache. Speak from experience. And so we're defining then what is, because we've not defined it from the one port, define pressure drop as out minus in, and then flow in as just Q.
At this point, you need to make a decision, but typically you want to know what goes into your systemic loop. So we define it based on the incoming Q. So whenever we interrogate systemic loop.q, we get the Q in. Because there's compliances in there, so Q in and Q out won't be the same. So you need to know what Q means for the elements you define. But we kind of always define the Q as the incoming flow. So if you look at the flow for an element, that's always the incoming flow. So if there's no compliance involved, that's obviously the flow through and out as well. But in this case, the flow through is not defined, because in and outflow are different.
So
that's a design decision when you set up your component system.
Yeah. So you compose that then just with the in pin, the out pin, and the parameters, but they're inherited from the already defined elements.
And now CRC is just an element like any other.
Yeah.
That obviously now has more parameters. So if you look at the parameters we need to give it, that is now C1, R, and C2.
Yeah, but they're the same parameters.
And then that can be used like any other element.
So we're going to go through.
Incidentally, CRC is already defined in the library, but it's an example of how you can make up your own subsystems, which makes it easier to compose larger systems. So if all your system is the same, you could even design the whole system as one, define a connection point, basically an API for your system, and just put an additional loop on those two connection points that you define, if you want to take it that far. But we have defined, for example, the whole 4 chambers.
Yeah, so we've got a heart element and things
so
like that.
If you want to follow the published G heart and want to use that and don't want to mess with the valve functions, you can just use that and define that once, and then play with different circuits and different combinations, different branchings, etc., without messing with this one element. If your systemic circuit is always the same, define a systemic circuit, leave it, and just use that as one element with 2 connections, which makes your connect tree much more manageable.
So same as before, we've got a chamber, left ventricle, and 2 valves. But now we're saying, okay, well, we want the representation of the systemic circulation to just be a CRC, and we're not really bothered we're not to write out the individual elements. So we just say, okay, systemic circulation is CRCR, and then we're connecting up, so we've got flow out of the ventricle into the valve, but the flow out of the valve then just goes into the systemic circulation there. So, and then flow out of the systemic circulation is into the mitral valve, out to the mitral valve, and into the left ventricle. So, while it's no kind of grand feat, I just want to get across that we can now control the level of granularity that you want. If you're solely interested in a kind of an aesthetic modeling purpose, then you could, as we'll see down, you can define an entire 4-chamber model in 3 lines of code in terms of defining 3 elements: heart, systemic, pulmonary, let it go. But if you want to perform you want to mess with individual parameters, then you may want a bit more, okay, I'm going to change individual elements, or you're playing around with different elements and adding different, taking away. Then it's important to define them individually.
We had 2 applications, for example. We played around with different additional loops in our circulatory system, but didn't want to worry about the heart. And if you look at the source code for CirculatorySystemModels.jl, you will find the she heart model in there, which has
it's in here as well.
Parameters,
yeah.
but you define it once, and you run it with a standard parameter set, which are all defaulted. So you only need to define that as one element and don't worry about it anymore. It has left in, left out, obviously, and right in, out, right out, because it has 4 ports.
We'll come to that. Yeah.
Yep. And then another application, we wanted to change the heart valves, which means we couldn't use that combined model because that has 4 fixed heart valves in there. So we couldn't exchange those heart valves.
You mentioned adding additional external loops
Yep.
to the system. Then are you also able to enforce additional constraints or
Yes, you can. If you have additional constraint equations, you can just add those into your connect system. So when you look at the connect system, just show me one, that's just ODE equations that come out there. So the connect function just returns the Kirchhoff equations. If you have additional constraints, you just put them in there.
And what about additional input functions?
Additional input functions for what?
So if I wanted to simulate some kind of stress on the heart or something,
Yeah.
because of some activity, how would I do adding that here?
You mean time-dependent resistances, for example, or valve defects or something?
Yeah.
I would, in that case, I would define a time-dependent resistor, which would, well, if we do that live, maybe, to just take the resistor. The definition of the resistor, and copy that out. Yeah. So just as an example, we have other examples that we use, so just put that somewhere. And the resistance now is a direct thing. So if we take, for example, R equals a function name. So if we say R equals...
Well, we show that in the valve, actually. Show it in the valve.
Yeah, in the valve we have it directly.
Yeah, so we can
let's
look
go
at...
to the valve, because there we have
We'll look at the valve, so...
Example. But you can define elements that call external functions. Because we have the time parameter in the element, so we can have a time dependency, we can... so that's the easiest way. So if we did that recently with time-dependent changes in the circulatory system. If there's a physiological change, like tilt up or down, then just define that as an external function and call it within an element, an outside pressure, for example. Or an increase in the resistance that goes up with time. You just define the resistor, but not with a fixed R parameter, but with R equals function name. And then you just hand over the function name to that element and define the function externally. That would be the easiest way to do it. Or you just define a new element which has an additional function that can even be an ODE. We go into valve functions later, which can get quite complex with callbacks and additional ODEs, etc. But you set those up separately from all the rest. But for additional stress on the circulatory system, for example, whatever your capillaries contract, so the resistor needs to be time dependent, you just define that as an external function and define a new resistor element which calls that external function. That's how I would do it.
Yeah. So we're going to move on to a more kind of advanced system that looks like this. So this is from the She again, but just the systemic loop. So if we wanted to model each individually, just draw your attention to this definition of the atria. So there's two ways in which that this can be done. One is either a kind of an explicit representation of the atria. So if we look in, scroll down.
Come on. MIT doesn't get good whiteboard markers as well. You can't complain. So that's ventricle. And if we look at the contraction of the atrium, that's essentially the same. It's defined in the same way, but it's time shifted.
Yeah.
So we have an addition. We only define it as, and so we have two parameters, tau1, tau2, and we have an e-shift parameter, which just shifts it in time. So that's the delay in the atrial contraction. So that's how we defined only one chamber, but we can use it for ventricles and atria with a shift. It's also, we can define that E shift as an external function, because there are some physiological processes where that time delay changes, particularly neonatal, when we go from parallel contraction of atria and ventricles to that more adult or time shift. So there are ways you can define these external parameters as external functions and then change them in time. Or you can just use callbacks in the final system and change it in time. So if it's just going to be, okay, now I have a heaviside function increase in resistance, then an alternative to your question earlier would just define a callback in the final ODE system at t equals something and just change the resistance, the external parameter, and then that should work as well.
So the Xi systemic loop, we then can define compartment by compartment wise using what we did just above with Nikolai. So we've got a CRL, and so CRL there just defined in exactly the same way. And then connect the equations as we've done. But this time, if we look at the equations, we've there got 7 differential equations in which you can pay attention and provide the estimates needed for what appropriate initial conditions would be for them.
Or if you're a mathematician, so you look at the equations. If you're not a mathematician, states of that system gives you that without the derivatives and without the equations.
So, but likewise, if you wanted to then condense that entire thing into a systemic loop and say, okay, if you're more interested in new parameter optimization methods or anything like that, and you don't want to mess about with the modeling side of things, just define a whole system and develop the new methods on that. Don't worry about methods and modeling at the same time. Take kind of well-defined models and then just apply the optimization procedures to that. So chambers, diodes, and then the systemic loop. Just look at that. So that there is essentially all the same code as what we saw in the first pass, but just now it's all inherited into one single subsystem that you can use freely. So I'll put that down there. And these now generate graphs as what you would expect.
At this stage, it might be interesting to look at the, when you do stuff like this, everybody wants a PV loop. Yeah. So for the plots, recipes that come with modeling toolkit allow you to do that quite easily without going into calculating observables afterwards.
Well, Valve will give us a better PV loop.
The Shemart will give you a better PV loop.
Yeah.
Okay, let's do that later.
Yeah. So this is now, we were talking about time dependent and area changes in terms of heart valves. So up until this point, we've just used the, okay, pressure difference valve all the way open and a resistance across. Pressure difference too small, boom, valve shuts, infinite resistance. But obviously that's not the way in which that's done. So we'll take it kind of really quite slow on this. So
this is a valve that is used in that Xi model, the advanced Xi model, and it's defined based on opening of the valve leaflets.
Yeah, so it's
this is published, a published model. These are the equations from the paper.
Yeah.
And Harry just took those equations and implemented it using our framework. So this is not our valve model, but this is just the equations we got.
So this is for we're looking here for the application of, okay, well, and the equations are written in terms of, can we compare, well, the pressures at the left ventricle compared to the first aortic sinus there. So they're saying, okay, so the flow through that aortic valve there is just some factor CQ times by this AR and the square root of this, the pressure difference there.
AR is the area ratio of the opening area to the full area.
Yeah. So
Q is a resistance factor, basically. We have the area opening, AR, and, well, the square root of the pressure difference.
So that area opening factor is calculated in terms of the cosine. So you've got 1 minus cosine theta, where theta is the opening angle of that heart valve. So it opens nicely and then closes. But the time-dependent part there, the dependent part, is this opening angle here. So the opening angle is derived from the second-order differential equation, taking into account varying different factors.
Yeah, so that describes the kinematics of basically that opening on that system. So we're now going into semi-mechanistic hypothesis.
Yeah, so taking into account varying factors. So the She valve here takes into account a pressure factor, a frictional factor, vorticity, and I can't remember.
So it's basically Newton's second equation in the rotational system. Left side is the acceleration, right side are the equivalent forces, or relative forces. So pressure difference.
Which force is driving?
The pressure difference times the cosine, basically.
So the pressure difference is the main one.
Pressure difference is driving it. We have friction in there, which is both fluid and the internal friction in the leaflet. It's just a parameter in this model. It's not fully mechanistic.
Yeah.
We're currently working on a more mechanistic model that allows you to give more physiologically measurable parameters to these kinds of models. But here, it's fitted models, coefficients for the pressure force. So we have the projected area. If we open the valve, if it's fully open, the pressure difference doesn't drive it more open. So there's a cosine in there. And we have friction, which has d theta dt in there, which is the velocity. So that's the friction term. And we have that kV is a coefficient for the pressure in the wake behind the leaflet. So that's the three driving force parameters, driving and damping force parameters that drive the kinematics of that valve. The paper is referenced in the definition of the element on GitHub. So if you want to look at that all the references are in the definitions and in the doc strings.
So we initially set out to implement this as kind of the same direction that we've done with all the other ones. So we say, okay, well, if we can define the forces and define the parameters in the equations, then surely this could just be another element that we add. But one of the big issues was that, yes, it opened, but as soon as it reached its kind of maximum opening angle, it then just began to spin continuously, because obviously the code doesn't know what you want it to do, because we'd not kind of implemented the explicit, okay, well, when it reaches this...
We don't have a doorstop.
Yeah, we don't have a yeah, that's a good way to describe it.
So it will swing over, and then it will swing back, or if your damping isn't strong enough, it will just go in a circle. Because all we have defined is the acceleration on that, like basically hinged valve system. So that's a big problem that we ran into this, and it's not part of the paper actually.
Yeah.
So the equations defined there is just ripping apart these forces and splitting them up into their different components, and then define the theta is omega, the omega is that function. There's a bit of Boolean in there because we don't want to have it, once it reaches maximum angle, we want to set it to 0. That's what the Boolean operations are there. And once it's at reset closing angle, we want to set the acceleration to 0. So that Boolean is an addition of two Booleans. So one is always 0 and the other is 1, so that is all right. And the next, then you calculate the area ratio, which is just this cosine squared equation, and then we just have the Q equation, which takes the coefficient, the area ratio, and the square root of delta P into that calculation of the flow rate. So the tricky bit for this valve is in the two additional, or in that one additional second order differential equation, which we've reduced in order by defining omega, and into two differential equations, and we had to introduce limits. So the limits function, the limits definition up there is for a callback, internal callback within that element. So if when the theta angle, the opening angle reaches maximum, then we set omega to 0. So then it stops moving. That's a hard stop. That's part of the published model, and we see that in the results. So it's a hard stop, it runs into a hard door stop, basically, and the same. So we have theta is theta min, then omega becomes 0. So we have two hard door stops in this.
Quick question. Does it have to essentially stops like that, placing cursor on the solvers,
You mean these hard changes? Yes, theoretically yes, but it's surprisingly robust. It makes it, differential equations JL is very robust in that. So it slows down around the callbacks sufficiently enough that we get away without using, is that correct?
Yeah.
Without using stiff solvers.
Yeah. So
these models take longer than the simple diode model, which is also a Heaviside function if you look at it that way. But these models take a lot longer because of the slowdown at the full opening and slowdown at its full closing. So it's not an order of magnitude, but it's 2 or 3 times slower than the simple hard models. Some of the more complicated hard models that involve more of these stiffening tricks, they can be an order of magnitude slower. So it depends what you want to do. If you want to do a quick run, go with a simple valve model. If you want to go what valve disease is, then you want to have a more complex heart model, and then that's the price you have to pay. But this, I didn't believe it would work with a simple callback like this, but it does. And
are these callbacks usually discrete callbacks, or are they also enforced?
It's this implementation continuous events, which is not a prescribed callback, but it's a callback when it reaches internally that, when the state, and theta is a state in this case, when the state reaches that callback, then it will hit it. It's implemented as this continuous event. Callback.
Continuous.
So it's not a discrete as in at a certain time, but it's dependent on a state callback. So not sure about the correct word here, but I don't think it's a discrete callback in that sense.
So parameter lists, all prescribed by the paper, but here all that is then contained in this she valve. So we say, okay, you want to use a more advanced heart valve, let's use the she valve. But the connections are essentially exactly the same. What we've changed here is from resistor diode to she valve and the respective parameters there.
So going from that really simple heart valve model to the more complex heart valve model is just changing those 2 lines. The rest of the whole code is still the same.
So if we just look at the equations that return to us there. So we've got 11 differential equations, but some of them are states as a consequence of using this more advanced heart valve. So, for example, like angular velocity and things like that.
I think we see the effect to what you mentioned, because we have that hard doorstop.
Yeah.
And that is very obvious from the results, but it's also in
Yeah.
the paper.
So there,
that there's basically the water hammer effect that we get as an interaction between the hard run into the doorstop and the inertia in the early systemic circuit. So we get that pressure oscillation there, which is a result of running into that hard doorstop callback. But these curves look exactly the same as what she had in their papers and described as a feature. It's the response of the ODE system to that hard heaviside function on d theta, d omega dt.
But these more advanced heart valves do have an advantage over the previous ones. If I just there, so there is one. This is exactly the same graph between two different systems. So one is the model, the simple with the systemic circulation with the diode valves. But then if we look at the one with She and She valve, the more physiological, i.e. the tracing between this aortic pressure and the ventricular pressure is much closer than what you see in most models. So it's a trade-off on what you want, because you'll suffer in terms of time, but in terms of actual physiology, it looks a lot better.
This is not about the valve model, but there's obviously potential for improvement in these valve models by having a damping function that makes that doorstop soft to get rid of that impulse reaction. And that's one of the people we're working on. We're trying to get a better heart valve model at that stage, which will require additional equations and maybe a damping function, and that instead of that setting it as a callback, adding damping function. But that makes the whole solution process a lot slower again, because it adds to the complexity of that valve function, which sits at the center of the whole thing. So we have these drawbacks and swings and roundabouts here with different requirements that we have. But yeah, there's definitely room for improvement. What we did here is implement the She valve as it is described in the paper. Well, in the paper, they didn't describe that they needed to stop it because we got a nice 360-degree heart valve if we do it without that, and the parameters that they have in the paper. So, and we see from the results that are described in the papers that there must be something like a step change in that heart valve. So our implementation and the paper are equivalent.
What was that little spike in the beginning?
So
that's the inertia of the initial.
This one there.
Yeah.
It's pressure, isn't it?
Yeah.
So the ventricle starts contracting, but the valve is closed. And in order to make it move, we first need to build up some force. So that is the valve is closed, it has rotational inertia. And in order to overcome that in rotational inertia, we need to build up an overpressure first. But that is something you do see if you measure the ventricular pressure. You see that before the valve opens, because there is that delay. That is physiological, but the oscillation at the closing isn't. So we need to overcome the initial inertia of the valve, and then it opens, and then the pressure drop over the valve goes back, and then it builds up as we accelerate when we go into that square root term. Because the resistance is dependent on Q squared. So once it starts flowing, resistance builds up, and that's where the pressure increase comes in again. But this first blip, that's just getting the heart valve to move from rest. Depends how you implement it. We haven't been successful in doing it yet. Yeah, there's two things here that go into how long it will take to solve the whole problem. How complicated is your damping? If you damp it with an additional differential equation, then that will add to the computational time. But at the same time, if you get rid of the impulse reaction, the oscillatory instability that's then damped out, that would speed it up again. So where is that break-even point? I have no idea at the moment.
So we'll look onto this kind of the full model, which is essentially a carbon copy of a systemic circulation also. And we'll go from a real kind of high-level view to simplifying that down all the way to just a few lines of code there. So if we wanted to add that pulmonary loop, we've now got two additional heart valves, tricuspid and pulmonary, that have the same dynamics as what we've just described up there. We've then got the right ventricle and the right atrium also. But, well, we've got she systemic, she pulmonary, there's no need for she pulmonary, but just for the distinction between the two, in that one is they're both the same loop with the same electrical components, but just for...
They have different internal names. So
yeah,
to identify the parameters.
Just so I don't go into a TISM or anything.
With one loop definition,
but they are exactly the same. And then we connect in, so we connect from the systemic loop now feeds into the pulmonary circulation, into the right atrium, out through the tricuspid, into the ventricle, out through the pulmonary valve, and then into that loop, all landing back into the left ventricle there. So, simplify that. And that then generates the same as what we've seen previously. So, this is then how we are, how do we create the she heart? So I'll spoil the fun and then go back to it. So we just want to say, okay, well, you want a heart, you want a systemic and a pulmonary loop. How do you do that? So in these 3 lines of code, we've got heart, systemic loop, pulmonary loop, connect them. And this time we've got 22 equations, but solve that.
The systems for these 3 previous implementations should be just the same. Because what we did only combine a few elements into one element and just build the system of those super elements or compound elements rather than from all the elements.
And so we've then got the she heart. So this heart then, we're defining additional pins this time. So we need, because we've got then 4 chambers in. But we now need 4 pins because we've got the left side and the right side. And how do you join them 2 up together? So define as what we've done previously, 4 chambers, 4 heart valves. But we start from, okay, we now need a left heart in. So what's coming into that left heart? And that goes into the left atrium, and then out through the mitral valve, into the ventricle, and back out the aortic valve.
The heart model has 4 external connectors. Left heart in, left heart out, right heart in, right heart out. And all the rest happens internally.
And then exactly the same for the right heart there. But just in them few lines of code, you've simplified all the specifying all the additional components with all the additional parameters. And you can focus solely on just saying, okay, well, 3 lines of code, give me 3 different elements, and I'm going to churn them out for you. So I could show the time-dependent resistance for the transitional model.
Mm-hmm.
Yeah.
Yeah, because that goes back to
Let me find this. I've just had a thought about.
to the question we
Yeah.
had earlier. If we want to, for example, while the code is running, or while the system is running, want to have a transition between resistances, for example, we have one case which we worked on recently.
Yeah. So the case for this is in fetal circulation.
Don't give everything away.
I'm not going to give
It's
everything
going to be
away.
on YouTube.
It's
It's not published yet.
No, but the model is, and this is only the published model. There's nothing new here. Is there ever? So this is from a kind of modelling the transitional period between, okay, fetus is being born, what happens when you kind of clamp this umbilical cord?
So there's a few things happening there. There's openings closing between the two atria. There's a hole in there that closes over 24 hours, is it?
Yeah.
And the umbilical cord is closed.
So this is...
And there's another shunt in the system between pulmonary and systemic circuit, which also closes. And I mentioned the time delay between atria and ventricles. That also develops in the early phase, in the early transition between fetal and neonatal circulation. So there are a lot of time-dependent changes in there, which is what was asked about earlier, how we can implement those.
Yeah, so this is where the... this is the model here that we're going to show there is. So this is a model for the fetal circulation where the blue is the additional compartments you have as a fetus, and the green is what expands after you've been born. So after you've been born, the pulmonary circulation kind of kicks into action, your lungs expand, and you start to breathe on your own. And so back to the actual point, is about saying, okay, when that fetus is going through the transition, do you clamp the cord immediately, or is there a delayed clamping there in order for certain reasons to occur?
I think the component that's most closely going into that question earlier is one of those shunts.
Yeah,
because
one of
that's a
transitional.
time-dependent function that's externally described.
So where are we? So here's one way in which I've done this here. So these are for the components which are closing, hence kind of...
That's defined as a component with an internal function.
Yeah, so we've defined this internally, it's kind of time dependent, in saying, okay, well, this resistance changes over time, and that time is inherited from the rest of the system, and we just say, okay, we've got a variable, because comparing to standard resistor, if I just... So standard resistor there is just given as a parameter. So this is something that you specify and it's just given to the system there. What we're saying is this resistance is now time dependent, and this is going to change over a certain period. So we have a time at which this resistance is activated. That would be the time at which that fetus is born, and it's kind of the clamping has begun. So you would then slowly increase the resistance on this umbilical cord there, and then tau F is the time at which that umbilical clamping finishes.
They're all defaulted at 1, which doesn't make sense.
Yeah, they're defaulted at 1, and then I specify the parameters further down. And so we just then specify an equation for that resistance. And you say, okay, well, the resistance changes over a period of time from there's an initial resistance, a final resistance, which is set to close to infinite in saying, okay, by the time this transitional period's gone, that the resistance in that vessel is no more. Nothing else is getting through that. And the time dependency includes through just writing it as you would kind of write it by hand almost. But that includes this kind of external forcing in saying, okay, you want that resistance to evolve, and it's then gonna shut.
So that is now using the internal function. I mentioned earlier that you can also do it as an external function if you want to change that a lot. An example would be the driven force or driven flow equation, which takes a function, which I used, like I showed in the introduction, and which Harry used earlier, where we had driven flow. We have the maximum Q multiplier, basically, and then we just give it a function that we usually just define between 0 and 1, which give you the flow shape. And that's an external function that's called. So for external functions, if you look at the driven flow element, that is how you can do external functions for any of these internal parameters.
And this is an example of kind of big systems that we're hopefully going to simplify down. So as I was trying to reproduce the results in this, and I needed to take control, I just specified individual compartments and said, okay, can I build from the individual compartments there? And so one instance which might be important to talk about is like...
there is work towards a GUI where you can click all these together. We need to think about how we can make circulatory system models compatible with that, but there may be in the future a graphical user interface to put all these components together rather than going through a hand sketch and identifying your connecting points and getting it wrong when you copy and paste element connections.
So here at the aortic arch, we have flow comes in from the ascending aorta there, but then is exited on 3 different bifurcations. So how do you include that in the connect statements here? So going into so the ascending aorta, we say, okay, well, flow ends up going in there. But from that, you just write it as individual connect statements, and you follow the line of the graph in which you're going. So here we say, okay, we'll connect the aortic arch out to the resistance of the upper body. So that's down there. So we're now on this path here. So we say, okay, resistance of upper body goes into the actual compartment of the upper body and into the superior vena cava. So that's just that line down there. But additionally, you could have a look at a different branch. So, yeah.
There is at this stage maybe important to mention you can connect as many elements you want with one connect statement. And that's how you had to do it in the early days of Modeling Toolkit. Now, Modeling Toolkit is really clever enough to just figure it out. If you connect element A and element B, and then in the next line connect element B and element C, it will figure out that that's a triple connection. So you can, when you extend your network, now basically do it completely naively, just, okay, I want to connect this to this, and the Modeling Toolkit framework will figure out if that actually connects to 5 other elements or not. So you don't need to go through that thing and then just rewrite your whole connect statements. But because you now have a branch that connects to multiple elements, you can just connect the element that you want to connect to the element you want to connect it to. And the system Modeling Toolkit, not our system, Modeling Toolkit will now figure that out for you. So that wasn't the case in the beginning, which made it a bit more tricky to get these connect statements in, but the new version of Modeling Toolkit since 8 point something actually is pretty clever in that. So whatever you do, it should give you a stable system in the end.
Yeah, and I just see as you're building these systems, it's an iterative process. And being able to write individual connect statements is almost vital in that model building.
So that makes it a lot easier to extend your system because you don't need to look at, okay, does that change my connectors? But you just add an additional connection.
If you add an additional branch or an additional bifurcation, you don't have to worry about that.
Like that, and you have, for example, R1, you have a compliance here, and you have R2 here. And I just add this additional compliance as a branch. I just need to connect it to the out of R1. But okay, in this case, it's easy to see that that's the in of R2 as well. But I only need to make that one connection. And the system will figure it out in the end. So it's much easier. And that also goes into maybe potentially making these connections automatically if you want to run parameters on automatically created structures. So add branches as you go along and see, okay, how many branches do we need to get convergence for a certain system? Do we need all the branches, or can I get away with 2 branches that then stand in for multiple branches? If you go down the capillary bed, that might be interesting. So you can see, okay, define n from 1 to 10 and see where do I get the good representation. So you could do some meta-programming stuff with that as well by just using that additional connect statement, basically create your connect statement automatically and all of that.
Yeah, so I was wondering, at what kind of fidelity would it become unreasonable to actually define these connect statements by hand, define these components?
I don't know. I personally find it not that difficult to do it by hand. Others are more visual and want a GUI to go with it. I personally don't find this any difficult. But yeah, if you have 100 connect statements, then yeah, it becomes a bit unwieldy.
It depends from which side you're coming at.
A graphic representation of a 100 connect network isn't easy to do either. Isn't easy to work with either.
Yeah.
For like IC designs, you end up with hundreds of thousands of parameters, right?
Yeah.
Completely unconnected. So
Yeah.
There's any analog.
Well, we don't have that many connect statements. So I think the most complex circulatory system models are 140-ish, 200 elements.
Yeah.
And since they're mostly serial and branches, so you have one branch, and then you have a series of 2 or 3 elements, combines resistor inertia, or 2 elements if you go further down and the inertia becomes less important. So you could define vessels, for example, and a vessel which we have, a CRC or CRL, is a vessel element. So you can define a vessel element and then just have a for loop defining 145 vessel elements and have a bit of logic in there to do the connection. So 1 goes into 2 and 3, 2 goes into 4, 5, 6, and you can build your branching tree based on the logic behind it in a meta loop and just do it that way. So if you want, or you just start out doing it, but it's hundreds of connections and not 100,000. So yeah, in that case, yeah, you would most likely want to automate things a bit more, but you can do that. So for these branching systems, which are important for going down into the capillary bed, because it's usually a branch into 2. We have a few branches that go into more than that, but it's usually branching 1, 2, and also you have usually these n branch elements, which you can predefine maybe, and then you have in the pulmonary, in the lung, for example, if you want to go away from blood circulation now, go into lung modeling, you could define the branches from the bronchia into the alveoli. That's done in a similar way very often, and you can define these automatically to have, okay, give me a branching tree with n daughters, n levels. And that will give you a connect statement for branching tree. So that is, it's a logical function, so you can implement it in code, and then you can just output that connect statement. Because the way the acausal modeling works in principle is you define a function, and that function gives you an ODE at the end. But within the function, and that's basically the compound model, within the function, the connect statement gives you an equation, not an ODE, but an algebraic equation. And then you combine that with the ODEs in the individual elements. That's what the expand statement does. So the first step is we define the connection model, because the circ equations is just the connect equation.
Yeah.
The second step is to compose the circ model, which is the connect model, the network model, with the ODEs of the components, or the vector that comes afterwards are the components. So all the components in your network go into that second parameter, or that second argument. That vector is the vector of components in your model. So you could create that vector dynamically, So, and then there's no limit, basically. Because you can create that first equation set in a function and then just export a dynamically created network model. Then you have a dynamically created component vector that goes into the second statement. So you can create arbitrarily complex models if you have a logical description how the model is developed, like it's always a branch or something like that, or it's always a connection from this to this, then you can dynamically create those. And then there is no limit to the number of connections. So I can easily say, okay, give me a branching tree of 256, sorry, I like powers of 2, 256 levels, and that gives you, how many? 2 to the 512 equations, I think, in the network model. Yeah? And that would be it. I wouldn't want to write those out by hand.
Yes.
I think that's the short answer.
So, should we go through this global sensitivity analysis? Because I think one of the big drawbacks that this acausal modelling front has is that when you do that structural simplify, obviously eliminates the variables and returns the ones that are kind of the easiest to solve in that instance. But then to perform sensitivity analysis, you quite often, well, you'd be very lucky if in your solution vector, which would be the states of that, are the ones that you're interested in. Because we may be interested in other ones that are not included in that state list. So they would be in the observed. But in order for us to access that observed, use that as a measurement, and then calculate that is quite a lengthy process. So the hard part in the sensitivity analysis is the solving of these equations. But then on top of that, accessing the observed variables, it can really slow the whole process down. So that is where it is sometimes better to write, well, until we've kind of done this, but it'd have been better to write your systems derived by hand because you can access the measurements from the solution vector directly, and so the differential equation solving is incredibly quick. The computation of the sensitivity analysis is incredibly quick. But we're saying, okay, if you want to use circulatory system models to perform a sensitivity analysis using any sort of measurements that are available, how do you do that, and how do you do that efficiently?
Here we see a trick. So if you ever need to use global variables in Julia, the traditional responses don't, but you can get away with it if you type them.
So this is our...
That's why all these parameters are typed, because then we have type stability further down the line, because otherwise it would slow it down by an order or two. So
this is purely just kind of a... best attempt.
This is just us being lazy, because usually you shouldn't use global variables.
Well, yeah.
We define all the parameters as global variables and just type them.
So this is our best attempt at this sensitivity analysis using this acausal framework that doesn't suffer from quite large time degradations. So we're looking at just the Xi systemic loop. So we'll look at just atrium, ventricle, and the CRL combinations.
So this goes now beyond what our library does and show how you can easily link that into the wider SciML framework. Yeah. Because what comes out of this is just a regular modeling toolkit ODE system. It's fully symbolic. You have all that in the background. And whatever you want to do with ODE systems after this, you can easily do. So what we did so far is just define the ODE systems and solve it. But parameter optimization, Optim.jl, whatever, global optimization, black box Optim, whatever you want to throw it at, you can do parameter optimizations in the classical Julia way. You can do sensitivity analysis, which is what Harry's working on. But that's not the point. What is global sensitivity analysis necessarily? What we're going to show is how you can then maybe make your life a bit easier, because one thing that we didn't know when we started this is that it will give you the ODEs in arbitrary order. So the state vector is not always the same. The parameter vector is not always the same. State vector, you can just address it with giving it the name. So sol.lv.p will give you the left ventricular pressure, even if it's not in the states, even if it's an observable. So that is, you don't need to address it as solution 1, solution 2, solution 3 for the states. So you don't need to index those through, because you can call them by name. And you can do similar things with the parameters. So I don't need to change parameter number 45, which is, I have no idea what it is, but I want to change the resistance in the capillaries. I have no idea what the order of my parameter vector is and what the resistance of the capillaries is in that vector. But Modeling Toolkit has cleverly, for that reason, introduced parameters not the way we have it now with parameter list, just global variables, but as a parameter map. So you create basically another vector, or a dictionary kind of thing. It's not a dictionary, but it's a parameter map. And so you define it as a parameter map, and then just can call the parameters in the whole optimization way by their name again.
So this is the chunk in there.
So that's just the regular stuff.
Yeah.
So you just run the, okay,
This is for the chunking of the global 60s, you know.
Oh, you're there already?
Yeah.
Yeah, that's very detailed.
Well, just in saying how we do the chunking, because this is, we're saying about the accessing of the individual variables, causes the substantial slowdown.
I'm not sure if that's actually the reason. I think that's something that we need to discuss with Chris a bit more. Where does that slowdown come from? We just found a workaround for address. Because if you want to do an optimization, you very often want to address the observables, because what you measure might not be in the state vector. And while you're doing an optimization, you call on the states. We found that to be much quicker than calling the observers. So that, but we don't know why that is. So, but and in another thing, if you do 100,000 cases in parallel, then you build up a solution vector, which is a vector of solutions, which are vectors of other things again. So you get that nested structure, and garbage collection gets in the way. So we kind of chunked our solution, our parameter space into sections, and then ran that in parallel.
There are definitely, I think, more efficient ways of implementing this. You could be directly using tensor operations, I suppose.
Yeah, well, but I think maybe that's not best use of the next half hour, because that goes a bit too far into the details of the implementation, and I hope we have a better solution in the future. But what I would like to show is how we can use these parameter maps.
Parameter maps.
So do we have a parameter map somewhere?
Down in the heart of the region.
There, for example.
Yeah.
So if all of these should stay the same, and all you want is, so we have all the parameters, which are 20 in this case, then we define the whole thing and run it. So if I now want to change only one parameter, so this initial condition, I think I haven't found a good way to actually map the state vector to the initial condition. So that is still a manual check. There will be a way most likely to map that as well in the future. because that's the tricky bit. If you get the initial conditions in the wrong order, then that is a problem. You only need to do that once, but the parameter vector is usually much longer. And so there you can use a parameter map. Maybe that's something to work on for the future, for the initial conditions as well, a mapping function there. But if we run that, and I want to rerun it, then you don't go through the whole process again, but you use the remake function. So just going to be old-fashioned and use the whiteboard. See if this works. And I'm going to get the syntax wrong. So remake takes a problem, which is an ODE problem, and then you give it new initial conditions or new parameters. So I think you give it P equals, and then you would need to give it the whole parameter vector. But if you have a subset of parameters that you want to change, or want to only change one parameter set, then you can do that. Is that a square for the parameter vector?
Yeah.
It's a square. And then like that. So I can now say, for example, heart, and then that's LV.
Yeah, so this was just me getting something that we can get traction on. So if you look, you can look at the parameters. We've got 86 of the full heart model. And if we just take the second one of that, so we see that's there just equal to 1. But if we want to change just any random parameter of that, you can specify the parameter symbolically. So we're almost accessing subsystems here of, so we want the heart and then the left ventricle, but this P0, and we want to change that then to 5. We can remake that problem with this specified parameter map. So we're just saying, okay, we don't care where that actually exists within the list, but we're remaking that with this specified parameter map. And so the new problem that's made has got that updated parameter value.
If you haven't worked with Modeling Toolkit before, you don't actually define the problem new. When you do a parameter optimization, you don't define a new problem, because that would incur likely more compilation overhead, just-in-time compilation overhead. But the remake function, just in that pre-compiled object for the ODE, changes the parameters or the initial conditions out. So that's the trick that you need to have for having that quick runtime for all your 100,000 optimization runs. So you just define the optimization with the loss function, with a remake function, instead of defining a new ODE problem, because a new ODE problem definition, so if you say P is ODE problem, that will sometimes need to be compiled again if you change the parameters. But if you use the remake option, then that compilation overhead isn't there anymore. So, and that is thanks to new developments now very easy, because if I have a subset of parameters, let's say I have a 100 parameter problem, but I only want to optimize 3. Then my optimization parameter vector is 3 long, but I would still need to provide the 100 element parameter vector to my remake. This new remake function now doesn't need that anymore. So that's also a recent development. So I only need to give it a parameter map with the 3 parameters that I need to change. So all the rest stays at their predefined values. And that's pretty clever, because then I can redefine my loss function as a function of a 3 parameter vector, create the parameter map inside that loss function, push it into remake, run the solution, calculate my loss function, hand it back to my optimization problem. So if you want to optimize 3 parameters, for example, your valve parameters to measure ventricular volumes and pressures, then you only need to define those in your optimization loss function, and don't need to worry about all the rest, because that's still the same. That's not our stuff, that's just some tricks in Modeling Toolkit that we learned the hard way. I want to give you, if you haven't run into those obstacles yet. So in your loss function, you basically would have an argument of P, which let's have it 3 elements. Yeah? Then you define P map is square brackets name of the first parameter equals greater, the right arrow mapping operator, P1, P of 1, the name of second parameter, mapping operator P2, name of third parameter, mapping operator P3, and then you hand that into remake problem, P equals P map, and then you run the problem again. Do whatever post-processing you need. If you want to integrate over pressure or want to optimize for pressure difference between two, or pressure difference over minimum over maximum pressure over time, you can do all of these operations in the loss function and then just return the loss or vector.
So I think we'll show the development of another one of these kind of time-dependent.
About 20 minutes.
Yeah, we'll wrap up. So I'll get the paper up. Up here.
We had planned that as an exercise for you to do, but I think we're running out of time. So let's just do another demo of how, and we haven't implemented that completely yet. Well, you have a working version, but it's not part of the library yet. So you find a new element, a new function in there, and we had done that. There was one question, how I think you asked, how do you include the outside pressure? Didn't you? The outside, the external pressure on a compliance?
No, the question was actually to show the external surface pressures, however, there are pressure values from 0 to 30.
Yeah. Well, in our compliances, we have 0 pressure on the outside. But if you, for example, have pneumothorax, then the outside pressure on any vessels that are in the thoracic cavity will increase. And you can easily do that. If you go to the CirculatorySystemModels, we have the one definition of compliance PB, I think, what's the name? We have defined an additional parameter, which is now no longer 2 pins. So we have a pin in, pin out, and we have pin EP. And then the rest of the definition is essentially the same, but the pressure is now PG, which is the gauge pressure, and the difference inside versus outside. So we can now put on that additional pin in that function an external pressure that could be the thoracic cavity pressure that increases after you have a traumatic shock. So that would be an extension of an existing element, but just adding that external pressure. That's important for coronary arteries, which have an outside pressure that's relevant. Obviously, you have a pressure inside your body, but we just set that as 0, so all the pressures are against that relative pressure that you have in your body cavities. But if you're standing up, then that might change, so you can put that as a gradient of pressure depending on elevation. You can put that as a reaction to a bullet wound. For example, when you have liquid collecting somewhere and adding on that pressure, how does the circulatory system react to that problem? So you can extend it easily with that kind of additional components. And you see that if you compare that with the compliance, it just has that additional pin and that redefinition of the pressure, and the rest is the same. So I can call for P for the external pressure, I can call for EP, and I can call for P, and I can call for the difference PG when I look at the results, because they're all individual output values.
So this valve function is one based on this single ventricle model here of of a neonate. So this valve function operates based on, where are we? Here we are. So it's based on a Bernoulli resistor, in that Bernoulli resistor is a kind of a function of the pressure drop is this Bernoulli resistance plus a certain inertia term there. But it's driven by the effective area of the valve. So you can imagine it as, whereas we, in what we'd shown before with the shear valve, in it had two kind of flaps that open and contracted. This one's more of a hole that expands. So it's all, this one's in terms of area more than anything else. So we see we've got an effective area which the resistance and the inertia is calculated from. So we've got a non-regurgent valve, looks like that. If the valve is regurgent partially, we've got some area that's left open all the time. So you can imagine that in a perfect working valve, it opens and then shuts completely, so there's no area for which any fluid can get through. If it's partially regurgent due to this incomplete leaflet closure, we've got some sort of minimum area which may exist, and there's an extension there to also a prolapsing valve also. But this is driven mainly by this sigma, where sigma is a function of these pressure differences here between. So there's a pressure difference for the regurgent valve, and then a standard one also. So it's a question of how do we take this description here, kind of half a page, in we've got a function that drives valve closing and open, we've got an effective area. How can we translate that into an actual tool or / compartment which we can use? So what we've got here is, firstly, the first equation is that sigma. So we can write that using the based on the different if statements there, and if you were to implement this through kind of a hand-derived procedure, you'd be writing kind of reams and reams of if statements based on if this pressure difference is less than this, if it's not. With the functions from Modelling Toolkit, we can write it just as in terms of these balls, in that if the pressure difference is greater than 0, we've got the perfect opening.
There's two ways to get these if-else statements in there. One is with Boolean operators, like this, which I personally find easier to parse than if-else statements. If you prefer if-else statements, then they are interchangeable. The if-else, Modelling Toolkit if-else, that is symbolic and translates through completely. So you can have multiple, piecewise defined functions and dependent functions of each other in these statements easily, which is terribly difficult to do in some other frameworks for A-causal modeling, like Selimel, or Selimel doesn't allow that, or Delicate maybe has something similar, but it becomes a bit unwieldy in my experience. But it's quite a powerful method to get these things in. And as you see, we didn't go through all the length with using Unicode to make it look like the maths in the paper. So this is something that wasn't there before, and it's just this one. So this is something that wasn't there before, and it's just this one additional function, and now we have an additional valve function that we can just replace in models that we had done all the other things with. The model exists, we run parameter studies on it, we run optimizations on it. So the only thing I now need to do is put that somewhere, define that function, change my one named line, and then run the code again without any other change. And I think that's a very, very powerful feature of modeling toolkit that we exploit here by being able to not worry about the whole system, which is, well, one feature of acausal modeling, but only focus on the one thing that we want to work on, in this case, this valve model, and just implement that. And what we're not going to show you here is our own valve model at this stage, but we're working on a mechanistic valve model, but we can focus on that. We don't need to focus on what is the impact of that change and those additional ODEs that we have in that valve model on all the rest of the system, because we don't need to care. We defined it once, and we only need to change the valve models out and run one line named AV equals our valve, or replaced with named AV is she valve, and we get two results that we can then directly compare, run differences on, etc. I think we have 10 minutes left, so I think we go into questions.
Yeah, no, absolutely.
Yeah.
Do you have a question just related to the if-else and apps?
Mm-hmm.
Do you know if modeling toolkit does it, when you have a discontinuity like that, does it insert like a softer version, or does it like insert
No,
a
if you just run equations on that, have you run that system?
No, okay.
If you run the system, and if you look at the equations are completely symbolic. That you show, if you do equations so exist, you can LaTeXify, but that doesn't really help because the LaTeX version still has these weird variable names in it, which makes it difficult to read. But you can get LaTeX output from it. But then you have all the long variable names with these subscript pluses that give you the parameters. But it has the if-else function still in it. So where are we? Yeah, there, for example, there's a Boolean in differential T AOV theta T. In the next line, beginning of the next line, there's a Boolean function in there.
Yeah, down there.
And that's basically an if-else. If you do it in if-else, you have an if-else as you have written it in the code in this equation.
So it doesn't, I guess where I'm kind of getting at is usually like with an ODE, you would want either to soften that discontinuity or put a callback there, like a zero crossing callback.
We found that we don't need to do that in this case, because differential equations is pretty clever at shortening the time step whenever one of those internal changes. Yeah, you don't need callbacks that often if you do it that way, if you have these if-else statements in your code. Yeah, if you do it by hand, you can't, and then you have to put callbacks in, switch something out. But it's all really transparent in this case. But that's, again, not our credit, but that's modeling toolkit and symbolics.jl that does that. So I guess internally it will do something like a callback, because it is an internal, it knows when that event happens. Or it's determinable, let's say it that way. Let's not anthropocize the algorithm here. It's determinable when that event happens. So yeah, it will internally be one of those continuous callback things that we used in the definition of the valve with the dynamics, that we have that doorstop event. So you can have callbacks internally, which you do not need to define in the overall system. And that's also something that I found incredibly powerful here, because when we defined the she valve, we had internal callbacks. The ODE system that we solve later on doesn't have a callback. That's all handled internally and completely transparent to the user. The user doesn't need to know that there's a callback in that valve function. Externally, you don't see that. Because the ODE problem is defined as problem equals ODE problem of equation system, comma, U naught, P and T span. There's no callback in there. The callback is all internal. So that is a pretty clever thing there. That's the 12 mathematicians in a box thing, which is in modeling toolkit, basically.
workshops, I noticed that most of the solves that were happening during the course of the workshop were pretty fast.
Yeah.
That's for a single simulation, of course.
It's a single simulation for, I think typically you use 30 seconds.
20 to
20 seconds. Yeah, 20 or 30 seconds is what we usually use. So 20 or 30 cycles, typically. And yes, they are pretty fast. I had it in my introduction for a simple 4-element Windkessel model. Python was 970 milliseconds. Hand-coded differential equation JL, so hand-coded differential equations definitions were 4 milliseconds in Julia. So that's, and the modeling toolkit version, the acausal or circulatory system models version was 2 milliseconds, or down to 1.7 milliseconds, I think, from 3.8 for the hand-derived ones. So even a hand-derived differential equations is slower than the acausal modeling. So there's nothing to be won sitting around the table with this mathematician and another one for 2 days and deriving the 8 equations that we have for a 4-chamber model, for a simple 4-chamber model, and then fixing all the negative signs in the wrong places, because you don't get it faster.
I guess I wanted to know, as you increase fidelity of the model and circuits that you're designing, how does this computation cost scale?
Good question. I haven't checked that, but it should scale with the number of differential equations. But it will always be favorable compared to other alternatives. And we found, and that's one of the reasons that you could explain at the beginning why we are here, why I'm now using Julia instead of Python or MATLAB. Because MATLAB has gotten a lot better recently with just-in-time compiling, but the right-hand side of the ODE is still interpreted. So if I use a Runge-Kutta solver, that's 5 explicit operations that all require the DDTs that are defined in a MATLAB function. And that MATLAB function runs interpreted. So ODE 4.5 is fast. But if that MATLAB function isn't, then I have won nothing. Python is even worse because MATLAB does partial JIT on that function now. So I only get 25 times speed up or 30 times speed up against MATLAB. But Julia compiles that ODE, the right-hand side, completely down to machine code and runs it as fast as it can. And Modeling Toolkit, kudos to Modeling Toolkit developer team here. That is really, really good at giving you an optimized ODE. So the ODE systems that you get out of that I get out of Modeling Toolkit and differential equations JL as a solver, I don't think there's a lot of options to get that any faster because the ODEs are optimized. It's not necessarily the ODEs you expect, because I get mixtures of pressures and volumes for these models that I would not derive the equations for myself. But there's plenty of examples of ODE systems that are solvable if you derive it in one way, and not solvable or completely unstable if you derive it the naive way, as you would because you want the number of ODEs in P, and not 1 in P, 3 in P, and 5 in volume.
Yeah.
But,
I just wanted to have you guys speak to the solver settings. Do you struggle with any of these to get it solved?
no. Not at all. Well, in some cases, yes, with a more rapid stops on the valve models, there may be one solver that is a bit quicker than the other. But SID5, Vern 7, 9, I haven't tried any higher orders, but and we are not using any stiff solvers.
Yeah.
We did not have to resort to stiff solvers unless we made a coding error.
What about when you're searching over parameter spaces?
Yes, there are cases.
Weird parameter.
Yeah, there are obviously parameter settings, parameter combinations, or well, sections of parameter space where you don't get solutions. If you do an optimization, or then you need to check for the return value of the solver, and just put something invalid in those result vectors, if you do an optimization. So, but yeah, there are cases where, but even then, differential equations.jl has that auto function. You know? So if it doesn't run with a non-stiff solver, it will try with a stiff solver. So yes, there may be a whole region of the parameter space that takes 100 times longer for a single run than the well-behaved part, but it doesn't break. Or if I argue, okay, those sections are the ones that I don't want, then I take that automatic solver selection out. And I say, okay, do Vern 7, which is my favorite. Do Vern 7 for everything and break early because I save time. If I have a parameter set that doesn't solve, then my hypothesis would be that it's most likely not really physiological. Or I kill the patient. And then I just disable that solution.
Maybe just a small thing concerning the hard stop and also performance. An hour ago, approximately, you said that it's not possible to implement the diodes in an ideal way.
Yeah.
If you have a look at the modalica implementation, it is implemented ideally using a characteristic curve. However, this leads to an algebraic loop with integer variables, and no tool is able to handle that. Modalica tools are, and that is better in terms of speed than the solution to the system. And also, the implementation of a hard stop in Modalica is quite sophisticated.
Yeah.
I would recommend to have a look at this.
Yeah, we're looking for, this Xi valve that we have now is the one as it is in the paper, which shows all that behavior as well. Yeah, we're looking for better ways to solve these stop conditions. So tangent functions and other damping functions are an option there.
It looks easy at first.
Yeah, it's definitely a hard problem. So we should talk later.
Okay.
Okay. Okay, thank you very much.
Cheers.